SpaceX revealed the sideways landing problem, and it's devastating. Structural bending exceeds 1 million Newton meters. Engineers must add 12 to 13 tons of reinforced steel to survive. What does this weight penalty do to Mars missions needing dozens of refueling flights? Worse, propellant sloshing requires massive baffles, adding even more mass. Can they solve this without destroying the mission? Welcome to Space Update 24 Hours. Let's dive right in. To understand why this matters so much, we need to go back to where this idea started. Elon Musk has been complaining about landing legs for years, and for good reason. On Falcon 9, those legs weigh around 2,000 kilograms. Now scale that up to Starship, a vehicle standing 50 meters tall and over 9 meters wide. The legs needed to stabilize that mass would weigh somewhere between 3 to 5 tons. Every single ton of landing gear eats into payload capacity. So why did SpaceX tolerate this problem on Falcon 9, but refuse to accept it on Starship? The answer lies in the Mars mission architecture. Getting to Mars isn't just one launch. It requires potentially dozens of tanker flights just to refuel a single Starship in orbit. Add 5 tons of landing legs and you're looking at multiple extra refueling missions. That's millions of dollars and weeks of delays per flight. SpaceX's solution was radical. Eliminate the legs entirely. Instead, they built Mechazilla, a 140-meter steel tower with robotic arms designed to catch a 200-ton booster out of the sky. It worked. But what about landing on Mars or the Moon, where there's no tower waiting? That's when engineers started seriously exploring horizontal landings. The concept sounds wild. Starship descending vertically, then rotating sideways at the last moment and touching down on its hull like a massive steel log. Some proposals added 4 Raptor engines mounted symmetrically around the body, with each Raptor producing 230 tons of thrust. Even smaller versions could theoretically control a sideways descent. The Moon looked particularly promising. Lunar gravity is 1/6 of Earth's, atmospheric drag is 0, and landing forces drop dramatically. But could the hull actually survive contact with the surface while lying on its side? Here's where the engineering reality hits hard. Starship's stainless steel skin can handle around 6 bar of internal pressure and massive aerodynamic forces during re-entry when the thrust is applied from below. But rockets are fundamentally designed as vertical pressure vessels. Apply thrust from the side and everything changes. The bending moment becomes catastrophic. Engineers calculated that a 50-meter structure with thrust applied 4 to 5 meters off-center generates bending loads exceeding 1 million Newton meters depending on thrust levels. What does that mean in practical terms? The hull would need massive reinforcement, internal frames, thicker steel plating, structural bracing throughout the entire body. Even a conservative 10% structural reinforcement on Starship's 120 to 130-ton dry mass means adding 12 to 13 tons of steel. Remember those landing legs SpaceX refused to add because they weighed 3 to 5 tons? This solution is 3 times heavier. The mission architecture that relied on eliminating every unnecessary kilogram suddenly gains over a dozen tons of dead weight. How many extra tanker flights would that require? How does that affect the economic model SpaceX is building? But the structural problem is just the beginning. Starship's fuel tanks are arranged vertically, methane on top, oxygen below. During a sideways landing burn, propellant would slosh violently toward the side walls. Without proper baffles, the engines would lose their fuel supply mid-burn. Falcon 9 uses small baffles because its tanks are relatively compact. Starship's tanks hold roughly 1,200 cubic meters of combined propellant. The baffles required to manage liquid oxygen, which is incredibly dense, during sideways maneuvers would be enormous. They'd need to withstand sudden shifts of hundreds of tons of fluid. Can you design baffles that's strong without adding another 2 to 3 tons to the vehicle? Then there's the control nightmare. Engines mounted far from the center of mass act like giant levers. A thrust imbalance as small as 1 to 2% between 2 engines creates powerful rotational torque on a 50-meter vehicle. The avionics would need to respond within milliseconds to prevent the ship from spinning out of control during descent. Modern flight computers are fast, but the margin for error becomes razor thin. One sensor glitch, one engine hiccup, and the vehicle could tumble. Compare this to vertical landing, where thrust naturally opposes gravity, and the control problem is relatively straightforward. Which would you trust your life with on Mars? The fuel penalty makes it worse. Falcon 9's landing burn lasts 20 to 25 seconds. Short, efficient, predictable. A horizontal landing requires sustained thrust or multiple correction burns to maintain attitude, counteract lateral motion, and keep the vehicle stable during final descent. Simulations suggest this could consume an extra 5 to 10 tons of methane and oxygen depending on the profile. Those propellant reserves must be carried throughout the entire mission, from Earth launch, through orbital refueling, across interplanetary space, and down to the Martian surface. How does adding 10 tons of extra fuel on top of 13 tons of structural reinforcement affect the payload capacity SpaceX promised? While engineers debate these future concepts, SpaceX is dealing with very real problems right now. On November 21st, they lost the first booster built for the upgraded V3 design, the same generation that was supposed to solve earlier issues. During a nighttime gas pressure test at Starbase, the lower section suddenly buckled. This wasn't even a static fire test with engines running. They were simply pressurizing the tanks when structural failure allowed gas to escape. The booster collapsed from the inside, looking like an explosion but actually caused by pressure loss. The entire vehicle was destroyed. Why did a brand new booster, built with all the latest improvements, fail during a basic pressure test? A few months earlier in June, Ship 36 was annihilated at the Massey test site. Engineers were loading propellant for a planned 6-engine static fire when a pressure vessel in the nose section catastrophically failed. The failure triggered 2 massive explosions that completely destroyed the upper stage and heavily damaged the test stand itself. These weren't minor setbacks. These were complete vehicle losses of hardware that took months to build. What's causing these pressure-related failures? Are they pushing the structural limits too hard? Is the stainless steel behaving differently than predicted under repeated cryocycling? Yet amid these failures, one area is advancing faster than anyone expected: the Raptor engine program. The original Raptor 1 produced 185 tons of thrust. Raptor 2 jumped to 230 tons at sea level and cut the part count almost in half. Now Raptor 3 is being tested at around 280 tons of thrust with chamber pressures near 350 bar, making it one of the highest pressure rocket engines ever fired. It's lighter, more reliable, and no longer needs external heat shielding because critical components are now protected inside the engine structure. With 33 of these monsters on a super heavy booster, total thrust is approaching 9,000 to 10,000 tons at liftoff. That makes Starship the most powerful rocket ever built. But what good is engine power if the vehicle keeps failing pressure tests? Meanwhile, Falcon 9 continues proving that reusable rockets can operate at industrial scale. In 2024, SpaceX launched 134 missions, over half of all orbital launches worldwide. In 2025, they've already surpassed 149 Falcon 9 flights, and they're on pace for over 150 by year's end. That's more than 12 launches per month sustained across the entire year. Booster 1088 flew its 9th mission in August. By mid-2025, SpaceX passed 500 successful booster landings total. They achieved back-to-back launches on Saturday and Sunday from Florida, deploying 58 Starlink satellites in one weekend, a new turnaround record. Why can Falcon 9 fly reliably dozens of times while Starship prototypes keep exploding during ground tests? So what's the verdict on sideways Starship landings? The numbers tell a brutal story. We're looking at 12 to 13 tons of structural reinforcement just to handle the bending stress. Add another 5 to 10 tons for propellant management and extra fuel reserves. That's potentially 20 tons of additional mass, 4 times heavier than the landing legs SpaceX refused to accept in the first place. The entire Mars mission architecture was designed around eliminating every unnecessary kilogram. Now engineers are considering adding back massive amounts of weight just to enable a landing method that creates more problems than it solves. Meanwhile, SpaceX keeps losing vehicles during basic ground tests. The V3 booster collapsed during simple pressurization. Ship 36 exploded before engines even fired. These aren't landing failures. They're happening while the rockets are still bolted to the pad. Yet Falcon 9 just flew its 149th mission this year and passed 500 successful landings. The contrast is striking. One system has matured into an industrial workhorse. The other is still fighting fundamental structural challenges. The Raptor 3 engine shows SpaceX can push boundaries. 280 tons of thrust at 350 bar chamber pressure is genuinely impressive. But raw power means nothing if the vehicle can't survive pressure tests. Will they solve the structural issues? Can sideways landing ever work, or is it just an engineering fantasy? What's your take? Should SpaceX keep pursuing horizontal landings, or stick with vertical descent and accept the weight penalty? Drop your thoughts in the comments. If this breakdown helped you understand the real challenges, hit that like button and share it with space fans who need to see these numbers. Subscribe to Space Update 24 Hours for more deep dives into what's actually happening at SpaceX. We'll keep following this story as it develops.